to the second inquiry question, which is organic substances. And this is my favorite part of the whole, like probably the whole of HSC chemistry. This has some of my favorite stuff in it, so get excited, but not too excited because it actually is kind of hard, but we'll see. So this is the syllabus. The inquiry question is, how's information about the reactivity and structure of organic compounds obtained? And it looks smaller than the first one, but this is a lot of skills-based stuff. So we'll just go through it quite thoroughly. So you get used to the kinds of questions because this is quite new, but I can almost guarantee you that there will be a question from this section in your HSC or your trial. Like, it's always worth lots of marks, and it's really good at distinguishing people who just learned everything and people who actually understand what's happening, because all the questions could be so diverse, could be so different. It's the skills that really matter in this part of the syllabus. So I'll go through that some more with you now. So first, qualitative tests of organic compounds. This is just how to determine different functional groups and different bonds. So the carbon-carbon double bond, it's the bromine test. We know this one. It will decolorize bromine water. That's the main one you need to remember. There's also this other test where the addition of permanganate, potassium permanganate, potassium permanganate triggers a change in color. Then you've got your hydroxyl groups, which are like alcohols, and you have your active metal test. So if you add it to active metals, it will trigger the production of gas. That's a really easy one to remember. Another one that some people like to mention with hydroxyl groups is adding like acidified permanganate or dichromate and seeing the color change, because alcohols oxidize obviously, and this will change the color. But this doesn't really work because other organic compounds can oxidize as well. So if you remember from your organic chemistry, aldehydes can also oxidize. So it'll have a color change if it's an aldehyde, but also if it's an alcohol. So like, that's not one of the best tests. That's why it's not written here. And then you also have that other test, which is adding steric ammonium nitrate to change color. And then you've got your carboxylic acid tests, and this is all basically stuff that you could do with a normal acid, so litmus paper, and also sodium hydrogen carbonate testing, which produces carbon dioxide bubbles. And then also ester test, so if added to an alcohol under reflux conditions, if it produces an ester, which is usually associated with like a fruity kind of smell, if that happens, then it's a carboxylic acid. So carboxylic acids, you can basically test its presence, I guess, with any acid test, so litmus, sodium hydrogen carbonate. That's basically it for that part. Now we're going on to my favorite part of the syllabus. So this is structural analysis techniques. So there's a little bit of theory behind this, but the most important thing I want you to get away from this lecture series is that it's the skills that matter. You could remember every single, there's no possible way you could know what they're going to ask you about. Like, it could be any organic compound ever that they're going to ask you about. And if you don't know how to interpret the graphs, there's no way for you to know what that organic compound is. So that's why it's really important to really hone in your skills in this section. So we'll look at 4 main things: mass spec, infrared spec, NMR, and then UV vis spec. But we'll mostly focus on the first 3 because those are the 3 that come up most often in these types of questions. So let's get into it. Mass spec involves turning a compound into an ion. What happens is an electron beams past through and it makes it into a bunch of smaller charged fragments, and these are then passed through a kind of magnetic field, and when they move through that magnetic field, they go in certain directions, and that helps determine their mass. So if it's a lighter mass, that magnetic field would move it more because it's lighter. If it's a more heavier mass, that magnetic field will move it less because it's heavier. So knowing the way that an organic compound breaks apart can help us figure out the different fragments and can help us figure out what compound is represented in one of these graphs. So I'll give you an example. This is what they look like. It looks like a bunch of lines around, and there are lots of different peaks and that kind of stuff. But the main things to remember are that the one furthest to the right, the furthest to the right peak, that would be our molar mass. So the largest fragment size is our molar mass, because yeah, that's just how mass spec works. Then the other lines are different fragments. So this one is the mass spec of pentane. So that 43, that really high peak there, that's 43. That would be a propyl group. So if you look down here, I did the maths for you, drew it out. That's what the group fragment will be. And then you also have the 29 peak, which will be a ethyl group. So those are two ones that come up really often in mass spec, just because a lot of compounds would have a group that's like an ethyl group or a propyl group. So knowing that 29 and 43 mean those things, sometimes they can mean something else if it adds up like that, but most of the time it will mean an ethyl and a propyl group. So just remember those numbers. They can be super handy when trying to figure out like the organization of an organic molecule. Like you'll know straight away that 43 means that there's 3 carbons, a propyl group, and you'll be able to figure out, like, it's super good to remember. But yeah, that's mass spec basically. Here's a practice question. So as I said before, the furthest one, which is that 88 over there, that is our molar mass. So that's the first thing you should look at when you look at a mass spec thing. You want to look at that molar mass, and here, when you look at that molar mass, you can rule out most of the options. Then the next thing that you need to look out for is the fragments. So that 60 is very important. You need to find out what that 60 means. So if we go to our little calculator and do a little bit of maths, so yeah, so when you go to your calculator, do a little bit of maths, you'll find out what all of those fragments mean. But basically, how I did this was 88 is either B or D, and D is iron sulfide. It cannot be mass spec'd because it doesn't fragment like that, so it has to be B. That's literally the way I did it. It's pretty easy to eliminate. So I eliminated A and C because it didn't add up to 88, and then iron sulfide is just impossible, so it has to be B. So that was like a really quick way to do it, but a lot of the time there will be like an obvious answer, and if not, then look at the fragments, look at what that 60 means, or that 27, or that 41. But yeah, that's all I really have to say about mass spec. Most of the time when you look at mass spec, you will be looking for that molar mass, and that can help a lot with determining how many carbons there are in a molecule. So yeah. Mass spec is often paired with IR spec. IR spec is for functional groups, determining what functional groups there are. So they store energy in the way that bonds vibrate, and when the infrared light strikes a molecule, it can be absorbed by these bonds, and it can cause them to move in a certain way before being re-emitted. And it's a similar idea to colorimetry, but basically we measure the wavelength of the lights that are absorbed, and this tells us what bonds were absorbing those yeah, what bonds are present. So I'll show you what it looks like. So on the left, that's basically what you get in your data sheet. So it has the wavelengths for different bonds, and then you'll be shown a graph that looks like this. So we call them peaks, those dips, even though when you think of a peak, you think of it going up and down. You call these peaks still, even though they're more like troughs. But yeah, an important thing to note is past 1,500, so this stuff here, that's called the fingerprint region, and we usually ignore the fingerprint region except for when there is a very distinct peak that just has to be mentioned. So most of the time that would be a CO bond. So when you see that distinct peak in the fingerprint region, that's the only time we can really read from it. All the other times we just ignore the fingerprint region and we focus more on the more defined peaks on the left hand side. So if we look at this what's it called? This IR spec here. We have that broad one, that broad peak here. And this looks like it's an alcohol. So it goes from 3230 to 3550. It sits on that range and it's pretty broad. So I'd say that that's an alcohol. Then if we look at the one next to it, around 3000, oh, it's probably going to be a CH bond because it sits in that range. So that means we have an alcohol, just a normal alcohol somewhere. We ignore the fingerprint region because then there's no big peak or anything happening on that side. It's just small peaks that are quite undefined. So we ignore that and we just take the information from this side. So the fact that there's probably an alcohol hydroxyl group and that there's CH bonds. So this tells us what functional groups there are, but it doesn't really give us too much information on the position of said functional groups or how many carbons there are, how many bonds that are alcohol, like how many alcohol groups there are, how many bonds there are. All of that information is not here. So we always need to use it with something else. So with mass spec, if we have it with mass spec, we could maybe find out how many carbons there are in this alcohol molecule and figure it out from there. Or if we have it with HNMR and CNMR, we can find out exactly the position of the hydroxyl group and the exact number of hydrogens, carbons, all that stuff. So you never just look at an IR spec on its own. So I started talking about NMR, which is nuclear magnetic resonance, and this is a little bit tricky theory-wise, but basically all you need to know is that it has something to do with how the nucleus spins. So if it's spinning one way and then it switches to spin another way, we can gain information on like what type of nucleus it is. That's a really simplified way of saying it, but basically because of NMR, whether it's CNMR or HNMR, which are the two main ones that you'll get in the HSC, when it comes to it, all that it comes down to really is that it gives us a diagram that can tell us exactly where everything is. And I'll go through how to read those diagrams in a second, but you can, like, these are the make or break diagrams. If you have a question and it has mass spec, IR, and NMR, you could just read the NMR and you could probably figure it out with a little bit of help from the functional groups IR information, but like NMR is just very comprehensive with the information that it gives you. So it's very important that you know how to read these, and I will go over that now. So HNMR, the trickiest part of Module A, and it's tricky because it has this thing called splitting, and I'll get to that later. But so first things first, when you look at an HNMR diagram, you want to count how many peaks there are. And by peaks, I mean like the clusters of peaks. You don't want to count the individual peaks just yet. Just want to count those clusters. So here you have 3 clusters, ignoring that TMS at the end. And those 3 clusters means that there are 3 unique hydrogen environments. So each cluster corresponds with a unique hydrogen environment. What that means is if we look at this HNMR diagram, it's of ethanol. And if we look at that, that diagram of ethanol, we will see the distinct hydrogen environments. So we have this hydrogen environment here, which is a hydrogen which is just bonded to an O. Then we have this hydrogen environment here. So both of these hydrogens are the same unique environment because they're both bonded to a C, and that C happens to be bonded to a C, and that happens to be bonded to an O. So they're both on the same unique hydrogen environment. Then the last one, it's 3 hydrogens sharing the same unique hydrogen environment, and that's because they're all hydrogens attached to a carbon that is attached to another carbon. So those are the 3 distinct unique hydrogen environments, and those correspond with the 3 peaks. Now, another thing that's important to remember with HNMR and also CNMR, which we'll get to later, is that the further to the left it is, so this OH, which is the furthest to the left, the further to the left it is, the more electronegative it is. So that OH is the most electronegative because of that O, because of that oxygen. The CH3 over here is the least electronegative because it's furthest away from that oxygen. So that's another important thing to look at when you're first looking at a HNMR diagram. So the 3 peaks means 3 hydrogen environments, and that one is the most electronegative. So once we figured that out, the next thing to do is look at the actual individual peaks. So this is splitting. Splitting occurs because of interference with the neighboring hydrogens. So you'll see that this hydrogen environment here, it has 3 neighbors, 3 neighboring hydrogens, and those neighbors will interfere with how this hydrogen is read. So basically what this means is if we look at the diagram, we'll see that the CH2, it has 4 mini peaks in the cluster. So there's 4 mini peaks here. Then in CH3 there is 1, 2, 3 mini peaks. And then here in the OH, it's a little bit hard to see, but it has 3 mini peaks. So you have the 2 small ones on the outside and the highest one in the middle. So the OH and the CH3 have 3 mini peaks, and then the CH2 has 4 mini peaks. So what happens in HNMR is the number of peaks in the cluster is 1 more than the number of hydrogens in the neighboring environments. So what that means is if we look at the CH2 here, it has 4 mini peaks. That means 4 is 1 more than the number of hydrogens in the neighboring environment. Yeah. So CH2, in the neighboring environment, we have 1, 2, 3 hydrogens. That is 1 more. That is 3. 1 more than 3 is 4, and that 4 is the 4 peaks. Does that make sense? So, like, there are 4 peaks, and in my head, 4 peaks means 3 gaps between. I like to count the gaps between. 3 gaps between means 3 neighboring hydrogens, which is 1, 2, 3. So that's that. Yeah, it's a little bit tricky to get your head around at first, but splitting is so important. Understanding splitting and understanding why it happens. First of all, I've seen a question in a past paper where they asked why does splitting happen. It just happens because of interference from neighboring hydrogens. That's all you really have to say. But understanding splitting, why it happens, and how to read splitting can make all the difference in being able to determine what molecule it is. So for this one, let's say the let's look at the other splitting ones just to make it make more sense. So the CH3, 3 peaks, which means 2 gaps, which means CH3, there's 2 neighboring hydrogens. That's these two, 1, 2, 2 neighboring hydrogens. Does that make sense? More sense, I guess. So yeah, you got the 2 gaps here, 1, 2, 2 gaps in the cluster of 3 peaks, and then that corresponds with 2 neighboring hydrogens. So I'll give you more practice on this. We'll do a couple of practice questions in a sec. But here's another example. So there are 3 unique hydrogen environments because there are 3 peaks. We have this peak here, and this peak here. The most electronegative one is a singlet. So how we name them is a singlet for a single peak, doublet for 2 peaks, triplet for 3 peaks, and so on. So this one has no splitting. It's just 1 peak, not a cluster of small peaks, so this is a singlet. This one here, least electronegative, has 3 mini peaks, so this one's a triplet, and so on. So there's no splitting, which means no neighboring hydrogens. So if we look at what the molecule is, which is here, which one has no neighboring hydrogen environments? Well, this one here has a neighboring hydrogen environment, which is this guy. And this guy has a neighboring hydrogen environment, which is this guy. So overall, this one has no neighboring hydrogen environments because it connects straight to an O, which connects straight to a C, and it has no hydrogens anywhere near there except for on that unique environment. So that singlet has to correspond with this group here. So hopefully that has made some sense, because splitting is a bit confusing, but as we do more practice, it'll make more sense. So now onto CNMR, which has no splitting, thank goodness. It's just an easier version of HNMR. And basically how we read this is instead of unique hydrogen environments, it's unique carbon environments. An important thing to remember, which I do think a lot of people get confused on, is just because it's a unique carbon environment, just because it's a unique carbon environment does not mean the number of unique environments corresponds to the number of carbon molecules. So sometimes you'll get a very symmetrical molecule. Let's take pentane, for example. Pentane has 5 carbons. So you've got 5 carbons just in a line, and that does not mean there are 5 unique carbon environments. There are actually only 3 unique carbon environments because it's symmetrical. You've got the 2 on the end, which are the same, 2, and then the 1 in the middle. So those are the 3 unique carbon environments of pentane. It's not 5. So sometimes the amount of unique carbon environments is less than the amount of carbon molecules. It's never going to be more. So it's read the same way as HNMR. The most left is the most electronegative, and it's electronegative because it's usually the most electronegative because it is bonded to an O or an N. So if we look at the diagram again, the most electronegative would be this carbon environment here. Then it would go here, and here, and then here. So those are our 4 unique carbon environments. The number of carbons in this molecule is the same as the number of unique carbon environments. So this is one of the ones where it's easy, but sometimes they like to trick you with symmetrical stuff. So just be careful with that. But yeah, so CNMR read the same way as HNMR, just no splitting, which makes it so easy to read. So just count the unique carbon environments by counting the number of peaks, and then go from there. So a practice time. it's a C NMR spectrum, and what gives rise to this spectrum. So if we look, you'll see there are two peaks, which means that there are two unique carbon environments. Two unique carbon environments means that it cannot be, let's look. Okay, so if we have 1,2-dichloroethane, that is one unique carbon environment because it's symmetrical. If we look at D, 1,2-dichloropropane, this would be three different carbon environments. So that is also out of the question. If we look at chloroethane, you have the two C's, and then you have one of them with chloride on it, and the other one is just full of H's. That has two unique carbon environments, because one carbon has a Cl attached, and the other carbon just has three H's attached. So that's in the running. Then, if you have B, which is 1-chloropropane, you have three carbons, and one of them has a chloride on it, and then two hydrogens. One of them has two hydrogens on it, and one of them has three hydrogens on it. All of those are different, so those are three distinct carbon environments. So the only answer to this could be A, chloroethane. So the best way to approach these questions is drawing out all of the options and then going through them and cancelling it out. So if you draw all of them, you'll notice that only one of them has two unique carbon environments, and that's your answer. So yeah, just draw them out. That's the way to do organic chemistry. Just draw it a bunch of times, and then you'll be able to figure it out. So that's CNMR. If we go back to UV Vispec, it's not directly mentioned in the syllabus, but you can also use it to determine some of the bonds. And you get a list on your data sheet, which is just there, and that kind of shows what wavelengths correspond with what bonds. The word chromophore could be a little bit confusing if you're seeing it for the first time in an exam, so just for context, it's a specific bond that produces a particular color, and you just use the formula sheet to figure out the answer. I have never come across a question where it has needed me to use that section of the formula sheet, but who knows, maybe this year will be the year they decide to chuck something in there like that. But yeah, you can just read it like how we read it before for that practice question with the concentrations. Very similar, except for this time you're paying more attention to what the wavelengths mean in terms of which bonds they correspond to. So I'll give you this other practice question, and we'll go through this in quite a bit of detail because this is what your HSC question would probably look like, or your trial question would probably look like. So here is the formula, C5H10O2. So immediately what you should be thinking about is whenever you see something that's O2, it could be one of two things. It could be a carboxylic acid, or it could be an ester. And based on the IR spectrum, we can figure out which one is which. So we'll get to that in a second. We have the formula C5H10O2, and then we have the HNMR, the CNMR, and the infrared spectrum. Before we look at HNMR and CNMR, we're going to look at the infrared spectrum, just because that can give us information on whether it's a carboxylic acid or an ester. And that will make all the difference when we look at the HNMR and CNMR. So if we're looking at the IR spec, what we'll notice is that there's a really, really messy fingerprint region over here, except for this pretty distinct peak here that I'm pointing at. And this one, it's about 1,250. And if you look at your data sheet, this corresponds to a CO bond. So this still doesn't rule out whether it's a carboxylic acid or an ester, but it's something to keep in mind. The rest of the fingerprint region we can ignore. Then we can look at this here. So if you look at your data sheet, you'll see that if it's an acid, it would have a really, really broad peak around here. We are not getting that. We're not getting that broad peak at all. This is a very skinny peak. This corresponds to the CH bond. So we can rule out that it's a carboxylic acid, meaning that what we're looking for today is an ester. So another way to confirm this is this peak right here. This peak, if we read the wavelength, it's about 1750. This corresponds with the C-double-O bond. This is in an ester, just as the CO bond is, so it's an ester, almost certainly. And it is, like, it's not an acid, so it has to be an ester. After we figure that out, you should, the next step, I'm not going to do this right now in front of you, but you should draw out all ester options for C5H10O2, all the different combinations possible, and then we'll rule them out one by one. So if we look at the HNMR spectrum, it very, very kindly gives the splitting pattern, so I don't have to count it. So in the HNMR data, we have a doublet, a singlet, and a septet. So that's 7. So that's a lot. And the most chemically shifted, so the most electronegative one, is 7 neighboring hydrogens. So that suggests that it has an environment on one side, an environment on the other side. It's not just one of those ones that's just one environment on one side. And then the oxygen. So that can already give us some information on what is happening here. Then for the CNMR spectrum, you'll see that there are 4 unique carbon environments. So CNMR has 4 unique carbon environments, HNMR has 3 unique hydrogen environments. Now, I'm not going to go through the entire process here. It's really just checking whether that splitting counts, but what I will do is, this is the answer. So I'll explain which parts of the molecule go with which sets of the data. So obviously it's an ester. I'm not going to name it because naming esters is confusing. Anyway, so we have this. Basically, if we look at the CNMR spectrum first, we'll see that there are 4, and here we can count 4 unique carbon environments. So first we have this one. This one is just a C that's connected to another C that's connected to 2 O's. So that's 1. This is another unique carbon environment here. This, pretty self-explanatory, another unique carbon environment. This here is another unique carbon environment. And these 2 are the same carbon environment. If we think of the symmetry, it doesn't look like it's the same one here, but if this was written on top here, then you'll see that they're the exact same carbon environment. They're the exact same carbon environment. So that's something to remember there. Now, if we look at the most chemically shifted hydrogen, the most chemically shifted hydrogen would be this hydrogen here. That hydrogen in there is connected to a carbon that's connected to an oxygen, and then another oxygen here. So it'll be the most chemically shifted. And we can see that that hydrogen has 2 neighbors, and those neighbors have 3 hydrogens each. So that's 6 hydrogen neighbors in total. Those 6 hydrogen neighbors, if you add 1, that's 7, which means there should be a septet. And that's exactly what we have as our most chemically shifted. So there's 7 peaks at the most chemically shifted cluster, and that means 6 neighbors, and that's what this hydrogen environment has. 6 neighbors for the 7 peaks. It's a little bit confusing, I know, but the number of peaks is 1 more than the number of neighbors. So the number of peaks, 7, is 1 more than the number of neighbors, 6. Sorry if that kind of confused you, but just remember, number of peaks, 1 more than number of neighbors. Okay, so if we go to the next most chemically shifted, it's a singlet, which means there are no neighbors, and that means it's this one here. This one has no neighbors whatsoever, because it's connected to a carbon that has no hydrogens on it, connected to an oxygen. There's no neighbors for this one. And it's the next most chemically shifted because it's closer to the oxygens than these ones are. Then, our last hydrogen environment, these ones here. So these ones, these two groups have the same unique hydrogen environment, again because of the symmetry. And these two have one neighbor, one shared neighbor, and it's this single hydrogen. One hydrogen neighbor means that there should be 2 peaks, and there are because it's a doublet. So that's the reasoning, and basically that's what you need to do in the HSC. So you basically just use the information, write all the possible ones down, and then just cross them off. Process of elimination is the best way to do it. Just go through all of the options and then find one that fits everything exactly. If something doesn't fit exactly, it's not correct. Because that's something that I did. I found an option that fit kind of like 50%, I'd say 80%. It fit everything but one section of the splitting. And I was like, oh, surely it was just a mistake on my end with counting the splitting. Surely this is right. But no, it was wrong. I put the barium in the wrong spot, or the chloride or something like that in the wrong spot. So it was completely wrong. But yeah, it's just really important to be careful with the splitting because that tells you exactly where everything is.